Okay, in the first part of this lecture 2, we have talked about lattice vibration of a monatomic chain. So now we look at one-dimensional diatomic chain. So basically, we have two atoms with different mass, but they are arranged in the one-dimensional and the periodical manner, right? So as you can see from here, the spacing between the two atoms, the nearest two atoms, is still A. But now you can see the two atoms. So one is in green color and the other is in red color. So the mass is different. So therefore, the periodicity of this lattice now is not A, it's 2A, right? Because from here to here is one period, right? So although the lattice spacing is still A, okay? So, so this means that the lattice spacing actually is different from the period of the lattice. Okay, now, in order to discuss the lattice vibration of this diatomic chain, so basically, we still need to use Newton's second law and also Hooke's law. So Hooke's law basically tells you the net force acting on each atom. So when the neighboring atoms are moving, all right, and then of course this is a restoring force, and then the Newton's second law basically tells you when you have a net force acting on this atom and how this atom will move. All right, basically we're talking about the kinetics of this atom. Okay, so now in the monatomic chain we only focus on one atom. So now for this diatomic chain, we need to focus on two atoms. So one is red and the other one is green. So now suppose we focus on atom 2s, that basically is this red atom, and then atom 2s plus 1, which is this green atom. Okay, so now this is the equilibrium state. And when atoms are starting to move from the equilibrium state, then we have this different displacement. Right, again, we use U to indicate the displacement, and then we use S to indicate the atom. This is the index of the atom. All right. So now, if we focus on this red atom, which is atom 2s, and then the Newton's second law basically is written like this. Right. So sorry, 2s basically this one. Right, in this one, and then the mass of the red atom is a small m, and then this is u, a second order derivative of u to s with respect to time. So this basically is the acceleration of this atom. Excuse me. Okay, so now the net force acting on this basically you can apply Hooke's law to both this displacement and then also this displacement, right? So, and then this is similar to the previous case. Now, you have two forces. So one is due to the relative displacement between these two atoms, and the other one is due to these two atoms. That's the reason why I have two terms here, right? So your U to S, you use ties here. That's because that we are focused on this atom. And similarly, for this green atom, it's a mass of a capital M. And then you can see that the two nearest neighbor atoms are this red atom, and then this is red atom. So one is 2s, the other 2s plus 2. So that's why you have 2s plus 2 and 2s here. And then this is the atom which we are focusing on. Okay, so now instead of one equation, now we have two equations. So again, to solve these two equations, and then we need to find a solution in this specific form due to the periodicity of the lattice, right? So this is very similar to the monatomic chain case. I will not explain further, but you can see for 2s, and then here you have a 2s and then QA, right? Basically 2SA is the distance from the reference, okay? And then for 2s plus 1, and you have 2s plus 1, QA multiplied by Q. So 2s plus 1a is the distance for this atom from the reference, right? And so once we solve the equation with the solution in this form, we can ensure the periodicity of this lateral vibration. Okay. So now we submit this U2s and the U2s1 into these two equations. And then we get this two simultaneous linear equations, right, of two variables, U02 and then U01. So U02 and U01 are basically the amplitudes, right? The amplitudes of the two vibrations. One is for the red atom, the other one is for the green atom. Okay, so now to solve these two simultaneous equations, and then we just, since the right-hand side coefficient are 0, so we just need to let the determinant of the coefficient matrix to be 0, right? This you learn in mathematics. And then, so the determinant basically is this element multiplied by this element minus this element multiplied by this element, right? With that, this be 0. And this is anyway, it's a very simple algebraic equation about omega and q. We will solve it, and then we find omega as a function of q in this form. Okay, so so here compared to the previous case, is a little more complicated because we have two atoms with different mass. So one is capital M, one is small m. And then the most important thing here that we have a plus and a minus sign here. So this means that we have two different types of dispersion curves. So one is this equation with a plus sign here, and the other one is a one with a minus sign here, right? So this will give you two different dispersion curves. So now, if we sketch this as a function of q, so this is what we have. So we have two types of dispersion curves. So one is this we call lower branch, which is this blue curve, and the other one is a red curve. Okay, in solid-state physics, and we do have a name for these two branches of dispersions. So the blue one we call acoustic branch, and then the red one we call optical branch. So we'll explain this one later, why we call this optical branch and then this acoustic branch, right? So now the first thing, you may have noticed that now the first Brillouin zone, we only show the dispersion curve in the first Brillouin zone. So the first Brillouin zone for this diatomic chain is smaller than the first Brillouin zone of the monatomic chain with the same atomic spacing. So, so now you can see that the first Brillouin zone for this diatomic chain is from minus pi over 2a to pi over 2a. You still remember for monatomic chain is minus pi over a, and this is pi over a. So it means that this is just half of the first Brillouin zone of the monatomic chain case, if the atomic spacing is the same, which is a, right? So why this is the case? This is because that for diatomic chain, the periodicity, the period of the lattice, right, in real space is 2a instead of a. That's the reason why the reciprocal space, the first branch zone becomes smaller, right? Because they are opposite to each other. Okay, so that basically is explained here. And then the dispersion consists of two branches, which so I already explained here, right? So now, if you look at the boundary, something is very interesting. So the dispersion is continuous inside the first Brillouin zone, but at the boundary of the first Brillouin zone, you can see that there's a gap. There's a gap between the maximum of the acoustic branch and the minimum of the optical branch, right? So the maximum of the acoustic branch is given by root square the internal frequency, okay? Root square 2c1 divided by capital M. And then the minimum of the optical branch is root square 2c1 divided by small m, right? And then the minimum of the acoustic branch, the frequency minimum is always 0. So when Q is 0 and then omega is 0. However, at the Q equals 0, your optical branch has a maximum frequency, right? Which is given by this, okay? So now, why we call this lower branch acoustic branch, and then the upper branch, optical branch. Okay, so now we just look at how the two atoms will vibrate over in these two different in two different dispersion curves. Okay, so now to understand this, we rewrite the two symmetry equations from previous slide. So we didn't do anything. So we simply copy it over, which is given here, right? So now instead of solving these two equations, we just try to find out the ratio between U01 and U02 from the two equations. So the first one is from this equation, and the second one is from this equation, right? So this is very simple. It's just an algebraic operation. You can calculate by yourself. Now, for acoustic branch, the maximum of acoustic branch given here, right? This is the maximum, which is the root square 2c1 divided by m. Okay. So now, if this is the case, and then you substitute this frequency, this means within this range. And so your frequency of the acoustic branch is definitely smaller than this one. And then the boundary will be equal to this one. So if that's the case, if you submit this frequency here, and then, so this term will always be greater than 0. Why? Because this will be 0 when this m is a small m, right? So, but when this m is a capital M, it means that this term will always be smaller than this term. So that's the reason why this is always positive. And on the other hand, and this one will also be positive. And then it will be negative only when omega 1 and q is at the Lorentzian boundary, basically this point and this point, right? So at this point, since the frequency is given by this one, you substitute this in here, and you find this is 0. And then inside this first Lorentzian, you find that this is always greater than 0. So this means that now if you look at these two equations, so from this first equation, so this one is greater than 0, and that's because we find out from here, right? And then of course, QA within this range is smaller than pi over 2, right? Because this is pi over 2a, then you substitute in, you get pi over 2, that's the maximum. And then within this range, so this argument is always smaller than pi over 2. And the cosine, if this QA, if the QA is smaller than pi over 2, this means this is in the first octant. This is always positive, right? So if this numerator is positive and the denominator positive, so this means that U01 over U02 is always positive. And similarly, you can have the same results from second equation, right? Because this is positive, right? Cosine QA is more than pi over 2. And then this is positive because you go from here. That's why from the second equation, you also reach the same conclusion. This means that U01 and U02, there is a ratio greater than 0. So what does this mean? So this means that U01 and U02 have the same polarity. So this means that when U01 is positive, and then U02 is also positive. When U01 is negative, and then U02 is also negative. So this means that these two atoms, you can see that the red atom and the green atom, they will move in the same phase, right? So the red goes to the right, and the green, green goes to the right, and then the red also goes to right. So if green moves to the left, and then red will also move to the left. So this means that they move together, okay? So this is for acoustic wave. And then, so of course, acoustic is really relative to optical modes, right? So now, maybe look at the optical branch first and then come back and look at this again. So for optical branch, you see what happens that this is smallest frequency is given by this. So that basically this one, right? That's the minimal frequency. So if you submit this into this term, and then you find that this 2c1 minus m omega squared will be smaller than 1, right? Because at the Lorentz boundary, this will be 0. But within the first Lorentz zone, this term will be larger than this one. That's why it's smaller than 1. And then similarly, you can find out that this one and this term is also smaller than 1, right? Because the minimum of your frequency given by this one, right? And then within the first result, definitely, so this one will be larger than this one, right? So that's the reason why it's also smaller than 1. Okay, so if that's the case, now you look at this from first equation. So this is negative, but this is still positive, right? So because QA is still smaller than pi over 2, so negative, positive, and then this reserve is negative. And similar for this one, so this is positive, and then this is negative. And again, you reach the same conclusion. So this reserve is negative. So this means that when U1 is positive, and then U2 will be negative. When U1 is negative and the U2 will be positive, they have opposite polarity. So what does this mean? This means that when the green atom moves to the left, and the red atom will move to the right, right? So in this case, what happens that if you have two atoms, for example, in real crystal, right? And then this atom basically they form a bonding, right? So the bonding can be in different forms. So typically for semiconductor, will be in either we call covalent bond or ionic bond. So covalent bond means that both will contribute the electrons. They will share the electrons, and the electrons are almost equally distributed. But even that's the case, and you still have some imbalance between the electron distribution. This means that one atom will gain a little more electrons from the other one. Of course, the other one will lose a little bit, right? And then for ionic bonding, and then basically that means that one atom will grab more electrons from the other one, and the other one will lose more, right? So in both cases, so this means that when one will be slightly positive charged, and the one will be negatively charged, right? So this basically means that this one pair of atom behave just like a dipole, right? So why is it dipole? Because one is positive charged and negative charged. So when this dipole move in this mode, it means that when they move in opposite direction, this means they become they're oscillating at a certain instant of time, and then this spacing becomes smaller. And then after that, they move in opposite direction, it will become larger. This is basically, you can see that there's oscillation of this dipole. So when you have an oscillation of electric dipole, so this basically will give you electromagnetic wave radiation. So this is the reason why we call this optical mode. So this means that when the vibration frequency is high enough, and then you get the optical mode. In fact, this optical frequency, this is the frequency of the optical mode is typically in the near infrared, in the infrared region of the electromagnetic wave spectrum. So that's the reason why we call this optical mode, right? Because it's like an oscillation dipole, electric dipole. And then for the acoustic mode, since both are moving in the same direction, and then it's just an average translation moment of the two atoms, and you don't see the dipole-like oscillation. So that's the reason why we call this the acoustic mode, right? So I hope you can understand this. Now, so why there's a gap at the first Brown zone? So what happens in this case? Okay, so now to understand this, actually is not so difficult. We just try to look at what happens at the Brown zone boundary. So why you have a gap here, right? So why this red curve cannot be in direct contact with this blue curve, right? So why you have a gap opening? So we have a gap opening. This means that vibration with the frequency within this range is unsustainable. So this means it's forbidden, right? Prohibited in the crystal. You don't have that kind of vibration with the frequency in this region, right? And then of course you have vibration with the frequency within this region. This means from here to here you have vibration, and after that there's a gap. There's a gap here, right, corresponding to this one. and then from this onwards, and then you have the vibration again, right? So why there's a gap here? So now we look at what happens at the boundary. For example, we look at this red boundary first. So Q is pi over 2a, so this is one, right? And then we can see that this omega plus is basically is the minimum of the optical branch, which is given by this, right? So now if we substitute this in, here, and you see what happens, okay? So first we find that, anyway, these two equations I just copied from a previous slide, right? The two equations before we solve it, two simultaneous equations, right? So now at the boundary, and then we find that, so this is not equal to 0. Why? Because this is a 2c1 minus m omega squared, right? So if you substitute this omega plus here, right, since this is capital M and this small m, so that's why this will not be equal to 0, isn't it, right? It's a non-zero coefficient. And then what happened to this one? So this one's in QA, and so you substitute Q here, and then you get cos n pi over 2, and the cos n pi over 2 is 0. So this means that this coefficient will be 0, right? So now you have this equation. And then this means that, of course, you can put U02 as 0, right? And then U01 as 0, and then eventually you will get 0, right? Or your U02 is not equal. So U02, sorry, if U02 is 0, but the U01 is not equal to 0, you still can satisfy this, right? But so physically, you can see that we cannot let both be 0. If both U02 in 0 and 0, basically you go to stationary case. This means none of the atom is vibrating, right? So that's why to satisfy this equation, and so we can let the U02 be 0, and then U01 is not equal to 0, right? So we don't need to require, anyway, sorry, maybe I put it this way. So once you have this equation, if you solve this one, and then so definitely you get a U02, right? U02, which is equal to 0, but the U01 we do not know, right? So U01 can be 0 or non-zero. You can still satisfy this equation, right? So, and then from second equation, you can see that, so this one will be 0. And that because cosine QA, the QA is pi over 2. Anyway, this is 0. And then this one, 2c1 minus omega squared, you substitute this one here, and then this will also be 0, right? So now, so you have this two equations. So from this equation, and then see what you can get. You'll get U01, right? So since U02 is already equal to 0 from fourth equation, and then from second equation, and you can have all combinations. So both U02 and U01 are 0, right? Or one of them is 0 and one is not equal to 0. So it means that U02 is 0 and U01 not equal to 0. Or U02 is not equal to 0, but U01 is 0, right? Or both are not equal to 0, but the both are not 0 is contradictory to this one because I already found U02 is 0. So that's why eventually, if you want to find a meaningful solution, this means at least the one type of atom or one sublattice is vibrating, and then so basically U01 cannot be 0. Okay, and so U02 equals 0, U01 is not equal to 0. Satisfy the two equations, right? For example, U02 is 0, substitute here, so this whole thing is 0. And then U01 is not equal to 0. You also satisfy this equation, right? So eventually, so this will be the so-called meaningful solution, right? And so what does this mean? This means that U01 is vibrating. U01 non-zero means that the red atom, because U01 represents the red atom, so red atom is oscillating or vibrating, but green atoms are stationary because U02 is 0, right? So it looks like what happened at this boundary that the two sublattices, so one is consisting of red atoms, the other one from green atoms. the two sublattices are decoupled from each other, right? So this means that when one is moving and the other one is basically stationary. Okay, this is what we have for this case, right? And then of course you get a high frequency. That's because only the atom with a smaller mass, which is oscillating, right? And then the one with a heavy mass is stationary. It looks like this heavy atom does not exist, right? Something like this one, right? And then you get the highest frequency, oscillation frequency at the first Brillouin boundary, which you can buy this one. Now, and then we look at the case that what happens at this frequency, but your Q is still the same, it's pi over 2a. And then what happens at this maximum acoustic frequency, which you can buy this one. And then we substitute in. So of course, I can see that this one, so look at this one first, okay? So we substitute in here, and then this one will not be equal to 0 because this is capital M, this small m, all right? And then, so this one is 0, okay? So cosine QA, because Q is the pi over 2, so this will be 0, all right? So in this case, if you solve this, and then basically, so what you will find, you basically get U02, which is not equal to 0, right? Sorry, we cannot reach at this. If I only look at this equation, I need to take this back. So basically, you can see that U01. So now U01 is 0 if you solve this equation, right? Because this is not equal to 0. So we get U01 is 0. Now, you look at this equation, and then so this coefficient will be 0 because it's capital M here. So this will be 0. And then similarly, so this cosine QA is pi over A is 0. So that's why this is 0, this is 0. Okay. So again, so in this case, you can only look at this equation, and then U02 and U01 can take any value. So you have a combination that both are not equal to 0, both are equal to 0, or one of them is 0. And however, since we already know that the U01 is 0 from this equation, so this means that in order to have a meaningful solution, and then we require that U02 is not equal to 0, right? And then U01 is 0, and then you still can satisfy these two equations. So, and then we reach this conclusion. So at this point, so what happens that the red atoms are stationary because U01 is 0, right? There's no oscillation. But the green atoms are moving, are oscillating. Since the green atoms will have a larger mass, so that's the reason why they give you a lower frequency. And then this frequency is different from this one. So that's the reason why, and then you have a gap here, right? So basically what you see. And so why you have this kind of situation actually is not so difficult to understand, right? So what happens in this case is that why you can have a decoupling between the two. So that's actually because that at this frequency, the interaction from the neighboring atoms are exactly canceled out with each other. So that's the reason why, although there's interaction, for example, if you focus on any of the green atom, right, you do have the interaction from the red atom. See this one. However, you can see that this red atom is moving in this direction, and this is moving in this direction. So the net force acting on this one is canceled out. So that's the reason why you don't see, right? You don't see any net force acting on this one. So this green atom will be stationary, right? And similarly, for the red atom here, so you can see that the green atoms are moving in opposite direction, right? Then, so basically you can see the net force basically is 0, and then they are canceled out, right? So eventually you don't see any oscillation of this red atom, right? So that's the reason why you have this. You have this kind of situation. Okay, so and if you some of you if you are working on graphene, and you know that the graphene has two sublattices called A lattice and B lattice, and what happens that at a special point we call gamma points, and sorry, K points, and then exactly and the decoupling of the two sublattice actually happens. So that's the reason why you have in graphene, you don't have the, for electronic property, you don't have a band gap. That basically makes a graphene very special, right? So it's quite similar, okay? Now, so just to illustrate this point, example, so here, of course, we don't use a longitudinal vibration, we use a transverse vibration. It's easy to illustrate this effect, right? It's something like this one. So you can see that the one atom is vibrating and the other one is stationary. Okay, so and then this is that decoupled, right? So decoupled is because that the net force acting on this one is always zero, right? So we have an interaction from this atom and also interaction from this atom, but the net force is always zero because the oscillate in opposite direction, right? So at the net effect, and then this green atom are not moving. Okay, you can have a similar picture for the red atom as well. Okay, so now, so when we derive this omega Q dispersion curve, right, for monatomic chain and also diatomic chain, we only focus on the longitudinal oscillation because it's easy to derive. And of course, that's the for monatomic one-dimensional atomic chain. But in actual case, in real lattice, in three-dimensional lattice, and then we always have a so-called transverse mode and then longitudinal mode, right? So what's the difference between a longitudinal and transverse mode? So longitudinal is defined in such a way that the displacement of the atom is parallel to the wave propagation direction. If that's the case, we call longitudinal wave, right? And the transverse wave means that the displacement is perpendicular to the wave propagation direction. It's just like this one, right? For example, this is a transverse optical mode, and then this is a transverse acoustic mode, right? So optical mode, you can see that these two sublattices are moving in opposite direction, and then and so this one, and they are moving in the same direction or with the same phase, right? So that's the difference. Okay. So of course, you can have a longitudinal optical mode and longitudinal acoustic mode as well, but for illustration purpose, it's always easy to illustrate this kind of transverse, vibration, right? So so this longitudinal transfer modes, of course, for both optical and then acoustic modes, you have a transverse and a longitudinal, right? So that's why you have a longitudinal acoustic mode and the transverse acoustic mode, and then you have longitudinal optical mode, LO, and the transverse optical mode, which is TO, right? So in general, the longitudinal mode will have higher energy. That's because that you need to push the atom away, and from the equilibrium position, right? It's difficult to push it in the longitudinal direction because you will see first you will see nearest neighbor, and after that second nearest neighbor. So that's why it's difficult to move the neighboring atoms. So that's the reason why you need higher energy, right? And the transverse modes are typically degenerate, right? So why this is the case? Because just look at three-dimensional case. If the wave is propagating in z direction, and then your transverse direction, of course, would be x and y. They are degenerate. There's no difference between x and y, right? So that's the reason why it's always degenerate. Okay, so we look at the real crystals and what happens. So of course, the real crystal will become much more complicated, right? And then you can see that this is a simple BCC structure, right? Body central cubic structure. So you have 8 atoms at the corner, and then they have 1 atom at the center, right? So all these atoms are interacting with each other. So the interaction at the first order can be approximated by a spring, right? So that's why I just try to imagine that or visualize you have many this kind of tiny springs which connect all the atoms together, right? And obviously, in different direction, your vibration will be different. For example, if you look at this atom, all right, and then the vibration in this direction and then this direction will be the same, and they still have another one right top, and then one as well. And however, and of course, this one also the same. However, the vibration in this direction will be different. Why? Because this atomic spacing is different from this one, or this one, right? So that's the reason why in different direction you will see different dispersion curve, right? So in general, if you have n atoms in the primitive cell of a 3D crystal, and then you will always have a 3n branches. Okay, so among these 3n branches, so 3 of them will be acoustic branch, and then the remaining ones will be optical branches. So it means acoustic branch number will be 3, and then optical will be 3n minus 3. So if n is 1, and then you don't have optical branch, that's like a monatomic chain, right? If n equals 2, like a diatomic chain, and then you will have this 3 acoustic branch and a 3 optical branch for the 3D case, right? So this is what you're going to see. So I already explained that in general, the dispersion curve is dependent on direction. Okay? Now, if you look at the silicon, all right, silicon has a diamond structure, right? And then each primitive cell has 2 atoms for silicon. Okay, remember for FCC, for the FCC, remember we also have for the FCC also 2. Sorry, I need to go back to check this one. But anyway, this for zinc blend, right? So you have 2 atoms. For the FCC is 1, right? Let me figure out. For BCC, so BCC in the conventional unit cell, you have 2 atoms, right? And so that's for unit cell. But for the primitive cell, you only have 1. Okay, you only have 1. So, but for zinc blend, and you can see that you have 2 atoms in the primitive cell. So that's the reason why you have 3 acoustic branch, and then 3 times 2 minus 3 optical branch. That basically is also 3, right? So that's why you have a 3 acoustic branch and a 3 and an optical branch. So for the acoustic branch, so you have 1 longitudinal mode and then 2 transverse mode. And the optical mode is the same. You have 1 longitudinal mode and then 2 transverse modes, right? And so now, since the dispersion curve in different directions is different, so that's why we have a quite complicated frequency spectrum, vibration frequency spectrum here. So, so this basically is the wave vector Q reduced wave vector dimensionless. What does this mean? This means that is the wave vector divided by the wave vector at the blue ransom boundary. So this means just normalize it, right? For example, from here normalize. That's why this is also always 1.0, right? And then this one is 1.0, and then this is 0. So this is 0, and then this is 0.5. Okay. So now, so all these numbers here, gamma and delta X, R, and K and sigma. So all this basically represents different high symmetry points in the Blue zone, because the Blue zone for 3D crystal basically has a 3D shape, right? So we will talk about this when we discuss about electronic properties of electrons inside the crystal. But here, I just try to understand that gamma is at the center of the first Blue zone, and then on the surface, or on the surface of first Blue zone, you always have all the different points with different symmetry, right? And then you just draw a line from a gamma, which is the center, to the different points on the Blue zone, and then you have these different directions, right? So the delta here tells you from gamma to X, you'll pass through these delta points, okay? And then along this direction, then you have this longitudinal mode, longitudinal acoustic mode, and then the transverse acoustic mode, right? So this transverse acoustic mode in this direction is a Q000. In this direction is degenerate. That's why you only see 1 TA, but actually you have 2 here, right? And then longitudinal, you only have 1 longitudinal here. For optical mode, and then you have a LO and then TO, right? And then TO is also almost degenerate, right, in this case, right? So now, if you look at this acoustic mode, they look very similar to the diatomic chain case, right? And the optical mode, and so for TA, and then you have a gap here, a large gap here, but for LO and then LA, for in this direction, you don't have the gap here, right? And then in this direction, this is from gamma to sigma to K to R, right? So all these are different directions. And you can see dispersion curve are quite complicated. But at least for acoustic mode, I can see that they are very similar to this diatomic chain case, right? So here, longitudinal LA, you can see the dispersion here, and then TA, two TAs, so here are non-degenerate, and then there will be will be degenerate only at this point between the overlap with each other, right? So again, you have a large gap between transverse modes, and there's no gap between this longitudinal mode between acoustic and optical modes here. And however, in this direction, so in this direction from gamma through this lambda to L, and then you can see that the TA is degenerate, and then you have LA here, and then you have TO and LO. And then again, in this case, you can see that you do have a gap between both transverse modes, transverse acoustic, and transverse optical modes, and also longitudinal acoustic, longitudinal optical modes, right? But of course, they are different from this diatomic chain case, because this is the simplest case in one-dimensional crystal, and this is three-dimensional crystal. But more or less, they are similar, right? Now, with this, we look at this phonon, which is we call the quanta of lattice vibration. Okay, we'll talk about we'll explain a little bit more about quantum mechanics when we talk about electronic properties. But here, anyway, we'll use quantum mechanics a little bit, but I will not give you any details about this quantum mechanics. And then, so why we need to do it in this way. So all of this, I will explain this one when we start to look at the electronic properties, okay? So, but anyway, to understand the phonon, which we will look at the oscillation of a simple harmonic oscillator first. So if you have an object in classical physics, you have an object, and so when you move this object away from the equilibrium point, and then if you have a restoring force, and this is basically just like a spring, right? For example, if you have a, and there are many of these kind of systems, right? So simple harmonic oscillator, for example, and if you have a, let me just, oh, oops, I don't know how to go back. Let me see where, so here, right? So anyway, so now, and so for example, if you have a flat surface here, and then you have an object which is connected to spring, and the spring is fixed here, for example, as a wall here. Then you just pull this. Suppose there's no friction, okay, and then you pull this object a little bit, and then after you release it, and then of course you will see the vibration of oscillation of this, right? So and of course you have many other examples. So what happens in this case that at the equilibrium state, there's no force acting on this spring or on this object. However, when you pull it or press it, and then you have force action on this one. So this force is always against the displacement direction, and it's also proportional to this displacement. If this is the case, and then you have this second harmonic oscillator, this kind of moment, right? So in classical physics, so basically is something like this one. M is the mass of the object, and X is the displacement, right? Displacement from the equilibrium position. Okay, and then so the net force acting on this is proportional to the displacement, and the proportional coefficient is C. But the most important thing is that the force is in the opposite direction of the displacement. So that's the reason why you have this negative sign, right? So if you don't have this negative sign, of course, you will not have oscillation because the object will be accelerated towards and it will move in one direction. It will not come back, right? So this negative sign is extremely important. It tells you that the phase of your accelerate the force and the displacement is opposite to each other. Okay? So this in classical physics. So if you solve it, of course, you get this simple oscillation, right? And in quantum mechanics, so for the same harmonic oscillator, and then so in order to describe this moment, what we do that we need to write down something we call Hamiltonian, which is an operator, right? So if you have studied quantum mechanics before, you understand what this is. If you have not studied quantum mechanics before, I will explain this one when we talk about the electronic properties of semiconductors, right? So now, and so when you use this harmonic, this Hamiltonian to act on something we call wave function, and then if you find that eventually you get another wave function which is proportional to wave function itself, and then the proportional coefficient. If you have this kind of solution, it's proportional coefficient, which basically will be the energy of the system, right? This is very simple in the quantum mechanics. Okay. So for this harmonic oscillator, and people have solved this. This is a standard textbook problem, and then people found that the energy of the harmonic oscillator cannot take continuous values. It can only take discrete values, and it's given in this very simple relation respect to the frequency, angular frequency. So the angular frequency is root square C or M, and M is the mass, and C is the first constant, right? We just introduced. And the N is an integer. So start from 0 and all the way to infinity, right? So now, and this N, when N is 0, so N0 basically is a ground state. So we can say that at the ground state, we still have a finite energy, right? In classic case, depending on where you will use a reference for the potential energy. If the potential energy reference is at the equilibrium point, and then actually at ground state, and this is no vibration, and then the energy should be 0. But in quantum mechanics, and this is not the case. This is because that due to uncertainty principle, and even at the ground state, there's a finite spreading of position and the wave vector. So that's the reason why you still have this, even at the ground state, we at 0 point, you still have this 0 point energy, which is given by 1/2 and h omega. Okay, and then the energy will take discrete values, and the spacing between the neighboring energy levels is simply h omega. It's a h omega, right? So that's a spacing. So the classical physics and quantum mechanics, they have a different, completely different picture. So now you can see in classical physics, so you can see that this spring, right, is attached to this object, and this object basically is vibrating, is oscillation, right? And then you can see the trajectory of this moment, okay? And you can visualize it. But in quantum mechanics, we cannot determine where the particle is, where the object is. And we can only determine probability of this particle in space, right? So what determines the probability? How to calculate the probability? And then we need to find out the wave function, which is basically the phi we just talked about. So once you know the wave function, and then then a wave function multiplied by this wave function complex conjugate, then this will give you the probability density for you to find this particle at any point in the space, right? But anyway, so this wave function, we look at this. So at different energy levels, then you have different type of a wave function, right? And so wave function in general is a complex function. So that's why you have a real part, which is blue, and also imaginary part, which is in red, right? So you can see that at different vibration modes, and then you have a different type of vibrations, right? So when n equals 1, so you have this kind of a wave function, and then when n increases, and then so basically you'll see that the wave function will have more zero cross points, right? So and then basically have a higher frequency, and so the higher frequency will give you the high energy, right? That's the basic idea. Okay, so now once we have this simple harmonic oscillator, and then we can apply this to monatomic chain. So for the monatomic chain, remember, we have used classical physics to solve this one. And so basically it's a Newton's second law plus Hooke's law, right? And then we have found out the dispersion curve for this, basically is omega as a function of Q, right? That basically determines the property, of this lattice vibration. So now in quantum physics and in quantum mechanics, and then we had to write down the Hamiltonian for this monatomic chain. So again, if you focus on each individual atom, and then so basically you have the kinetic energy operator and the position energy operator. You put together, you have the Hamiltonian, right? So now since we have this in this monatomic chain, we have many atoms. So that's why we just need to add all together. So this will be the Hamiltonian. So if you use this one to act on the wave function, and then you let this be another function, which is proportional wave function, and the proportional coefficient will be energy. If you solve it, it's very, very much involved. That's because that is different from this single harmonic oscillator, and then you will have so-called coupling terms between xi and xj, right? If you expand this one, so this will make things very complicated, right? It's not just a simple sum of the Hamiltonian of all these single harmonic oscillators. And to solve this, and of course, people have found a way to do that. And then instead of solving this in a real domain, and then you can do a Fourier transform, and then you go to Fourier space, and then you can effectively remove the coupling between and the displacement of neighboring atoms. And by doing so, then you can solve this equation. And of course, you can find this one in standard textbooks. We'll not go to details. So eventually, and people find that for this atomic chain, then the only difference that you just need to apply this periodic boundary condition, the one we introduced previously, right? And then you just assume that this monatomic chain can be divided into segments of n atoms, right? And then just repeat this n atom segment, and then you can construct the entire monatomic chain, right? If you do this, then basically, as we explained before, the wave vector will be quantized, which is given by tau n pi divided by Na. So Na is L, is a total length of this segment, right? Now, so this Qn basically will define the concrete or discrete vibration modes. So once you know this, so we can substitute this Qn into this dispersion curve here, which we derived using classical quantum mechanics, classical physics. Okay, and then you get the omega n. So because Q is Qn, and then omega n. So once you know omega n, and then you substitute into this equation. This is actually for a single, single harmonic oscillator, right? And then substitute in, and then you get the energy, get the quantized energy of this monatomic chain. So this means in principle, and then you still can solve it, okay? And then this frequency, this h omega q actually is corresponding to the energy of the phonon, right? And similarly, this h qn will be corresponding to the momentum of the phonon. This means that in quantum mechanics, so eventually, just put in a simple way, so in classical physics, eventually what do you get? You get this omega q dispersion, right? For a monatomic chain, you know that you basically get something like this one, right? Right, so this basically is the first ground zone. So this is what you find out from classical physics. And then omega q is basically is what you need to know in order to define the lattice vibration inside this monatomic chain. For the same problem in quantum mechanics, so what do you find? You find that so energy is given by, is quantized, okay? It's given by, so 1 over 2 plus n, and then h and omega n, right? Sorry, and omega q. So omega q you can calculate from this dispersion curve, okay? And then similarly, you have momentum. So because now what you have is not a wave, it's a phonon, it's a quasi-particle. So this quasi-particle has an energy, and it has a momentum as well. So this momentum, let's see, if you want to use n, you get n. So it begin by h, q, n. So that's the momentum of the phonon. So now in classical physics, what you get a wave, that's a lattice vibration wave. And then in quantum physics, what you get a quantization of the wave. So basically, it's a quasi-particle. When we call quasi-particle, means that it's not the real particle. Okay, it's a quasi-particle. And this particle will have energy, is given by this relation. And then I have a momentum as well. So once you know this, so now this whole thing is a vibration. Now what you have a phonon. It's just a quasi-particle, right? It has a momentum as an energy. So then you can use this one to describe the interaction between this phonon and the other particles, for example, electron and then the photon. So will make things very simpler. So that basically this picture, right? So the quantization of this lattice vibration is called phonon, right? And so in classical physics, and then there's a lattice vibration basically a wave, right? And then so in this quantum mechanics, and then you get a phonon. Okay, so the phonon will have wave vector q. So when this interact with the quasi-particles, for example, so here put neutrons here, photons here, electrons here, right? And so basically they'll transfer the momentum, and then the momentum basically given by hq. Okay, so this is a momentum, and right, but this phonon actually, this basically is not the real momentum. It means that it's not like when the center of mass which is moving, and then you get this kind of linear momentum in classical physics, right? Anyway, it's a quasi-particle can carry this momentum. It's mathematically, when we discuss the interaction between this quasi-particle and the electrons or photons, and then we just use this as a momentum, right? And then to follow the momentum conservation and the energy conservation rule, and then we can describe these interactions, right? Say for example, if you have if this is a electron, so this electron has a wave vector k and the energy ek, and this interact with this phonon. The phonon, you remember, this is a lattice vibration, right? And the quantization of lattice vibration is a phonon. So it has a wave vector q and then energy h omega q. Okay, so when this interact, and if this phonon is absorbed by this electron or photon, anyway, you can treat this as a photon or either photon or electron. Anyway, it's just another particle. And then so this particle will gain additional energy, which is hq, because it absorbs the phonon, right? And also the wave vector will change, right, from k to k from k to k plus q, equal k prime. So this means that the momentum will increase. There's a particle with momentum, because initially the momentum is hk. So now the momentum is hk plus hq. So because this hq is the momentum of the phonon, right, is absorbed. And then, of course, you may happen that during this scattering, right, you may emit phonon as well. So when you emit phonon, so this is the initial state of the particle, which can be electron or photon, right? And then if it emits a phonon, it means that you get additional photon with a wave vector q and then energy h omega q. In this case, and then energy has to be conserved. So now you can see that this particle, after scattering, energy is will be smaller, right? The difference is this hq omega q. And then similarly, the wave vector, now you get this difference, right? Because you emit one photon, right? So So basically, now you can see that I hope you can understand this picture. Say, for example, if you don't have this concept, right, and then what do you have? So basically, just try to imagine that. So you have a one wave, say for example, it's an electron wave, and then you have another wave, which is a phonon. And then these two will interact with each other. How to describe this, right? So in classical physics, it's very complicated, right? The two waves. So one is electron wave, another is a phonon wave. It's very difficult. But in quantum mechanics, and we do that, the wave basically is a particle, right? So it's a particle. And then this is also a particle, right? So a particle with a certain momentum and energy. So they interact. We just use classical physics, just like a collision between two objects, right? And then you follow energy conservation law and then a momentum conservation law, and then you can find out the end state of these two particles, right? So that's why the mixing is much simpler. That's the reason why we need this quantum mechanics, right? So this idea actually is general, okay? So it means that when you talk about the interaction between the two waves, it's always difficult. However, if you quantize the wave into quasi-particles, use a quasi-particle to represent each wave, and then it's much easier to understand how they will interact with each other, and then to describe how they will interact with each other. This means after interaction, you can easily find out the end state of the particle, right? So we'll learn more about this in the later part of this course when we talk about electron transport and also optical properties. Okay? So that's all about this part of lattice vibration. And then in next lecture, we'll talk about the electronic properties of semiconductors.